LeetCode 10, regular expression matching, isn't just an interview favorite. It mirrors real-world challenges in compilers, search engines, and live text filters. We're not just matching letters, we're interpreting logic behind Regex engines. With dot and star in the mix, it's easy to lose your footing. But stay with me, because smart matching beats brute force every time. Let's get into it. All right, ducklings, time to flap into our first approach. Classic recursive backtracking. It's not fast, but it lays out the entire decision tree loud and clear. We'll kick things off by calling a helper method from the main function, passing both strings along with indices to keep track of where we are. This gives us a setup to walk both inputs one step at a time. First checkpoint inside the helper. If we've hit the end of the pattern, we only return true if the input string is also fully consumed. That guarantees a full match. Next, we check if the current characters align, either exactly or with a dot in the pattern. This gives us a Boolean that we'll use for the next move. Here comes the wildcard twist. If the next pattern character is star, we've got two paths: skip the whole char pair, or if there's a match, consume one input character and try again from the same pattern index. If no star is coming, we can only continue if the characters align. In that case, we just step forward in both the string and the pattern. This brute force approach runs in big O of 2 to the power of m plus n, which balloons fast, even on short inputs. It also eats up big O of m plus n space from the recursion stack. It's powerful, but can crumble with deep nesting or lots of stars. So how do we cut down repeated work? Right? Memoization. Let's trim the fluff and speed up by caching overlapping subproblems. To save redundant calls, I'll drop in a hash map to remember results from earlier recursive states. With our memo map ready, we launch the recursive match again, this time starting from index 0 in both strings. Inside the function, we'll build a key using the current string and pattern indices to uniquely represent this subproblem. Before going deeper, we check if we've already solved this exact case. If it's in the map, we just return the saved answer. Now for the base case again. If we've hit the end of the pattern, we return true only if the string's also fully consumed, a clean, complete match. Before branching, we test whether the current characters match, either directly or with a dot wildcard. That result guides our logic. We'll define a variable to store the outcome. Whether we go left or right will depend on if a star is coming up next. Now for the core logic. If a star follows, we try two routes: skip the char combo, or match one input character and loop back to try again, if they align. If there's no star, we just move forward if the characters match and the rest also aligns from the next positions. Once we've computed the result, we stash it in the memo map so we don't redo the same work later. Finally, we return this result back to wherever it was called and let the recursion chain play out. Memoization slashes time down to big O of m times n, a huge win over brute force. Even maxed out at 20 and 30 characters, it stays under 600 steps, way more efficient, and no ducking around. But let's go further. Recursion still brings overhead. Each call adds to the stack. A bottom-up dynamic programming table helps us sidestep that entirely. To build the table, we need the lengths of both the input string and the pattern, since each combo will become a table cell. We'll create a 2D Boolean table where each cell answers: does S from I onward match P from J onward? Our base case is when both strings are fully used, so we set the bottom right cell to true, signaling a full match. Now we fill the table in reverse, from end to start, because current answers depend on later positions. At each cell we ask, do the current characters match? Either they're the same, or the pattern has a dot. But we skip this check if we've already run off the end of the string. Next, we deal with a star. If the next pattern character is star, we try two options: skip the star and its partner, or if the characters align, let the star cover one character and try again. If there's no star next, we only proceed if the characters match, and the rest of the strings match starting from the next positions. Once all entries are filled, we check the top left cell. It tells us if the full string matches the full pattern from the start. This DP method also runs in big O of m times n time and space, but skips recursion entirely. It's clean, stable, and perfect when stack depth is a concern, whether in interviews or production code. We began with raw recursion. Great for exploring, but too slow to scale. Memoization sharpened it by cutting out repeat work, dropping us to big O of m times n. And finally, we streamlined everything with bottom-up DP, avoiding stack overflow and boosting efficiency. That last move isn't just clever. It's what real engineers do to scale Regex engines, text filters, and search tools. Turning recursion into iteration is a must-have skill at top tech interviews. So here's your challenge. Take this mindset, apply it forward, and keep building systems that scale. Keep learning, keep quacking, and stay sharp out there.